Very good. Okay, so let's see. Last time we were talking about rules of inference, and what's coming after this section is just applying everything we have learned to be able to write some proofs. Okay. If you have never written proof, I'm not really going to expect that from one day to the next one you'll be able to write original arguments on your own. But at least with the knowledge that you have, you should be able to read a proof and tell whether it's a well-written proof or even if it's a valid proof or not. Okay? And then, of course, you should be able to prove some very simple statements. So we're going to start practicing on that. But before we get there, let's finish our discussion from rules of inference and arguments that we started last time. So let me just remind you that remember an argument is just a sequence of propositions, and then what did it mean for an argument to be valid? So an argument is a sequence of propositions. The last proposition we call it the conclusion, and then an argument is valid if already given, so you never question the validity of the assumptions, okay, of the premises. The first propositions are called the premises. Given that the premises are true, can you deduce then that the conclusion is true? If that's the case, your argument is valid. Otherwise, it's not valid. Okay? And a systematic way of checking this is you have your argument, then you can write the following conditional, take all your premises, do the conjunction, all of that implying the conclusion, and then just show that it's tautology. How you show that? You can do it via a truth table or just using logical equivalences. Okay? So we talked about this last time, and then we wanted to move away from truth tables if possible, because if our argument is long or has a bunch of little variables, you're going to have a huge truth table. You don't want to do that. Okay. So we introduced this notion of rules of inference, which are small little arguments that we know that they are valid, and then we can use those to be able to understand more complicated arguments. Okay. So we can use this like a little building blocks to understand the validity of more complicated arguments. So I'm going to be referring back to this list as we do the problems, and at some point you should be able to know this. Okay. So remember, I expect you to be able to know this. And anyways, in the exam, when I give you a question on this, I will provide this to you. Okay. Because what if you forget a little detail? So the question is, can you use them? Okay, can you use this at your advantage? Okay. So, for example, remember 8. Among all of these, 8 is probably the most strange one. Okay, and like the hardest one to remember. So, anyways, let's go ahead and let's finish this example. We did example A last time. Let's do B and C. Okay. Let's just go through example A really quick, just to get a warm up on this situation. So we're given an argument. We're given 3 premises and a conclusion. And then our job is to decide whether this argument is valid or not. Okay? How do we do this? I basically just gonna start writing a series of statements, all of which are true, and then the hope is that eventually they will lead me to the conclusion that we want, being a true statement as well. Okay? Along the way, you will use what you know about logic and also the rules of inference that we have above. So let's see. We begin with one of the premises. In this case, we know R implies S is true because it's a premise. Okay, so we begin with that. Then we can use our knowledge of logic to break this into an OR statement. So if this is true, then this OR statement must be true because they are equivalent, right? Remember, R implies S is the same thing as not R or S. Now, why do we do this? Because now we have this OR statement that's true. We have this third premise over here, R or G, and when you match these two together, you can now take advantage of the rule of inference number 8. That tells you that if you have 2 OR statements in which the first piece is a statement and is negation for the other one, then you can deduce the OR of the last 2 pieces. That's what this is telling you. Okay? You can kind of ignore the piece, and then you have Q or R. This, let's see, I just thought about something. This, for example, negation, you can think of it as being minus. Like the opposite of something, right? So you can think of that as P and then negative P, and think of OR as addition. Basically, what's going on here is that you are canceling the P's, and then you end up with Q plus R. Instead of plus, it's just OR. Do you understand what I'm saying? In other words, if you have P plus Q, and then plus negative P plus R, what is this? Q plus R. As you know, you cancel the p's, and then you end up with q plus r. Okay, so that's basically what's happening in number A, but at the logic level. Okay, so we don't have the issue to start and so on, but you can sometimes you can find these sort of analogies to hopefully remind yourself of what's going on. Okay, so we have that, and then we managed to obtain these two statements, and therefore using rule of inference number A, then we can deduce S or G because the R's cancel. Okay, now yes.
Why do we ignore the P and the G?
And very good. So, and now I'm gonna get to that. The point is that the second premise is not really needed. I mean, you can have as many premises as you want. Nobody can stop you from putting premises. Now, is it needed? No. P implies G has no business here. It has no business. So if I remove this, this still will hold because we didn't use it. Okay. So that's an extra premise. So it doesn't mean that you have to use all your premises. Okay. It just means that if you want to prove this, you can only work with what's given to you and your knowledge from logic. Like we were not given this or statement, but we could deduce it from here. That's fine. Okay? But you cannot make stuff on your own. Like for example, you cannot tell me, oh, R is true. Well, I don't know that. Because we're not told that, and there is no rule that would allow us to deduce immediately that R is true. Okay? Now, do you have to use all the premises? No, you don't have to. Okay? It's just that if you're going to use something, it has to be from here and stuff that follow from here. That's it. Okay? So that's the point. So here, P implies G, it has no business in what's going on here. Okay, so don't use it. Now, how do you know? Well, you need to do the argument. Okay, and the only thing is practice. And again, by doing problem, that's when you get the ability to be able to see what are the steps that you need to do. For example, I know I want to deduce S or G. So looking at this, I see an S over there, and I see G in these two statements. Okay. So somehow I want to make use of that. I see that it says R or G, and you need to go through your rules of inference. And you should realize that number 8 allows you to have an OR statement and then another OR statement with a negation, and then cancel stuff and deduce this. Okay? That's what hints to the fact that, okay, if I have this, I would like to see if I can come up with negation R or G, so that then we can deduce this. Looking at what you have left, this has no R, so I don't even look at it. This one has an R, that's good, and an S. Okay? And then you know that it's the same as not R or S, and then everything follows. Okay? So that's how it goes. It's like, for example, if you have done calculus, it's like integration. When you're given an integral, you just have to look at it and then see what method can you use. What is it? What technique, what trick can you use to make it work? Okay? There is no set path for a problem. Okay? All right. Anyway, let's keep practicing. Let's do B and let's do C. So, any questions about A before I move on? No? We did this last time. Now, let's do B. Let's see. We're given 3 premises, and then the conclusion is therefore S. In other words, after all of this, we need to be able to deduce that S is true. If we manage to do it, the argument is valid. If we cannot do it, then the argument is invalid. Okay? Remember, our job is to show that this is a valid argument. Okay, so how would I go about doing this? Well, you want to deduce S, right? So somehow we better use our first premises. It's the only one that has S. Okay? But to get to S, I have to get rid of P and R and all of those implications. Okay? So, for example, what can we use to be able to get rid of those? Well, notice that here I have a P. Let me revise it here. So, B does, the argument is P implies R implies S, and negation R implies negation P, and P. We have all of these, therefore S. Okay, so my job is to get here to S. I can do that by getting rid of P and R. Okay, so I will try to break these implications. Now, among the rules of inference that we have, there is one that allows you to break implication. What is it? Look at the rules of inference. What does the first one says? If you have an implication, and if you know that the first part of the implication is true, what can you deduce? That the second part is true. You see that? That allows you to break an implication. So let's see, do we have something like that going on here? Right, yes, we do. I have this implication. Think of this one, okay? So focusing on this implication now. and I have P. So you have an implication, you know that the first part is true, therefore this is true. You understand this? The rule of inference number 1. So I'm gonna begin my argument like that. So my argument, the arguments are just gonna be a sequence of propositions, okay? A sequence of statements. You need to justify why they are true. So I'm gonna begin by saying that P implies the implication of R of S. Whenever I write something, I mean that's true. How do we know this is true? Well, this is a premise. We don't question premises. Premises are given to you, they are true. Okay? Now, what else do I have? Well, I know that P is true. Once again, why? Well, this is a premise. Right? That's premise number 3. You see that? Now, if you combine these two, what can we deduce? So what will be my third point? What can we deduce from here? Therefore, R implies S. What do we use here? Rule of inference number 1. Remember, when you do this stuff, have this list next to you so you can refer back to it on the exam. I will give you this list so you can refer back to it. Okay? I use number 1. Okay? All right. So far, we know that R implies S is true. Okay? Notice that that was not from here, but we deduced it. Okay? All right. So at least we're closer to S. Now, it's always good to do some wishful thinking. What would you need to know, or what's one thing that you could know, or that you would like to know, so that you can deduce S?
How is true?
Exactly. So if we, here this is a way of breaking implication. If you have an implication and you know the first is true, you can get the second, right? So if you have this implication, if I knew that R is true, then I can get S by using rule of inference number 1 again. You understand this? So I'm gonna now try to see if I can somehow argue that R is true. If I manage to get that R is true, then I know I will be done because I can combine it with this and get that S is true, and we're done. Okay? So I'm gonna shift my attention to R now. All right? So let's see what we have. Well, we already used the first one, but now here there is something that has R. Yes? So what can we do here?
Use a feature, like P being true.
Good.
Because not P of the true P means it's false, and not R has to be true.
Okay, so let's play with that a little bit. We know that P is true, right? So now I would like to have P in here. In other words, I would like to somehow change this stuff around. Can I do that? Can you change an implication around? How? Contrapositive. Because remember, what does a contrapositive says? If you have P implies Q, that's equivalent to not Q implies not P. You can flip stuff, but you have to negate both. Okay? So I'm gonna go that route. So you can actually see what's gonna happen when you use contrapositive. You flip them and negate, so you get P implies R. With the P, you get your R. And once you have your R, you mix it with 3, and you get your S, and we are done. And you see the end. Okay, so that's the game that we're gonna play. So number 4, I'm now gonna take this. I know this is true. Remember, this sequence of lines that I'm writing, what I mean is all of these are true statements. Okay? Why is this one true? You need to justify. Why is this one true? It's a premise. Remember, we don't question premises. Now, what is it that we're gonna do after this one? Remember, when I use P, but to use P, I need to have a P in here, right? So now, because this is not R implies not P, I know that from here I can get P implies R. Why? Contrapositive. That's the contrapositive of number 4. That's why you should label the steps so that when you justify, you can refer to your previous steps. Okay? This is true because this is the contrapositive of number 4. Remember, contrapositive means flip and negate both. So the negation of the negation P is P, negation of R is R. Do you understand this? Okay, so now we have P implies R. Okay, we have P implies R. Remember our job. Our job is to get to S, but we've shifted our attention to R. So how can I get R if I know P? Do we know P? Yeah. Yes, we do. So if you want, we already have it there. So you can say using 5 and 2 by rule of inference number 1 that use R. But sometimes, it's nice to just repeat it just to have it clean. Okay, I'm just gonna rewrite this one down here. Okay, and just rewriting. I don't have to justify because I already justified this step up here. Okay, and now we use rule of inference number 1. So that will be my 6th deduction, which is, what can we deduce from here? Therefore, R. Why? As rule of inference number 1, right? It says that if you have an implication and you know that the first part is true, then the second part must be true. Are you following so far? Okay, now we have R is true. Now what do we do with this? So we mix it with 3, and what do we get? S. That's what we want, right? So I'm gonna rewrite 3 in here, which says R implies S. Again, don't need to justify. I already justified above. And now mixing these 2, we can deduce S. So my 7th deduction is therefore S once again. So here in this argument, we basically just play with the premises, rule of inference number 1, and there was one line which we needed to use our logic knowledge, the contrapositive. Okay? Sometimes you may need to use more than one rule of inference, but here we just use the same rule of inference multiple times. Okay? So the moral of the story is rule of inference number 1 allows you to break up implications. So if you want to get to the second guy, you can break it, but then you need to know to break it, you need to know the first guy. That's what this is telling you. Okay? When I get rid of this, if you know the first one, then you can do and you can get the second. Okay? So try to have that mindset. Okay, anyways, we started with, we wrote here a bunch of statements, all of which are true, and we were able to arrive to our conclusion. Therefore, S is true. So the truth of the premises implied the truth of the conclusion. So what do we know about this argument? So this is a valid argument. Okay? So this is a valid argument. Okay, questions? Do you understand this? Again, you need to sit down and do problems. If you don't do problems, there is just looking at this, there is no way that you can, manage this. But you have to practice. Okay, so that was B. So this one was, let's see, this one was valid. This one also is valid. So let's see. Let's go ahead and let's try C. So C. I'm gonna let you stare at it for a second and then see if you can find, a way of doing it. So not P, and P implies Q. Remember, here, at least in this course, anything you say, you need to justify it. Okay? If you say that is valid, you need to tell me why. Why is it valid? Well, for example, in this one, well, here it is. Here's the proof. Okay? If you say that it's invalid, you need to tell me why. How do you say that something is invalid? You have to give me a counterexample. Look, when P is false, when R is true, and when S is false, this breaks. What does it mean to break? Your premises are true, but then the conclusion will be false. Okay? So let's keep that in mind. Okay, so those are our 3 premises, and the conclusion is therefore not R. Okay, so think about it for a second. Okay, so what do you think? Is this valid or invalid? Huh?
Invalid.
Why?
Because R could be true. I mean, R is true.
How do you know that?
Well, first thing I did was use the rule of inference number 1 and
Okay, with what? With what premises?
with the first 2.
No, be careful. To use rule inference number 1 to break this implication, you need to know P. Do you know P? You know not P. This is not P. Right? You don't know P. You have to be careful. Yes.
I don't know which rule I use, but not B. For not B, you can think that P has to be false because not B is a premise. Because P is false, Q, and P implies Q means that you can be false or true. In the case that it's true, Q implies R has to be true, and not R will make it false.
Okay, so remember, if you say that it's invalid, instead of telling me a big paragraph, you just need to tell me, look,
Yeah.
with P this, Q this, and R this, it breaks. So tell me.
P is false, Q is true, and R is true.
So P false,
Q true,
Q true,
R true.
R true. Okay. So your classmate is claiming that this is an invalid argument, and to justify that it's invalid, all you have to do is give me a counterexample. What does that mean? Tell me a specific context in which this fails. Okay? What does it mean to fail? And then we're gonna get into, okay, why would you think that it's invalid? And then that's the stuff that you're telling. But if you're gonna justify, you just have to tell me this. Okay? So let's verify that this will be this is a counterexample. In other words, for this to fail means that we have to make sure that with these values, the premises still hold true. You have to make sure that your premises are still true, but that your conclusion is false. Just remember, validity means that given the truth of the premises, you can deduce the truth of the conclusion. So a counterexample would mean something that will keep the premises true, but give you a false conclusion. Do you understand this? So let's see, let's verify. So this is, the claim is that this is a counterexample. Okay, and then let's verify. Let's see, premise number one, that's negation P. So in this case, that would be the negation of false. What's the negation of false?
True.
True. All right, so we're good. Premise number one is true. Okay, let's verify premise number two. So as P implies Q. Okay, so with these values, we will have false implies true. What do we know about this?
True.
This is true. So premise number two checks out. Now let's check out premise number three. As Q implies R, which in this case would be true implies true. Yes? So what is this?
True.
True. So premise number three checks out. Now, hopefully I can say here, but, so the three premises are true, but the conclusion, which is negation R, we're expecting this to be false, right? Or this to be a valid counterexample. Let's see. That's the negation of true. Okay, good. This is false. So this means that the argument is invalid. Okay? In other words, here is a case in which your premises hold true, but we didn't manage to deduce the truth of the conclusion. So this is an invalid argument. And this is when it breaks. It could break in all situations. Okay? But this is a case in which it breaks. All right? For example, something else I was thinking, you can also, another counterexample would be the same thing, but then with Q false. If you make Q false, that also is a counterexample. Because notice that, because P is false, this implication is true regardless of Q, right? So according to this line, remember when the beginning is false, the implication is automatically true. Yes? You just have to make sure that, whatever Q you pick, make this one works. And if I pick Q equals false, that's also make this implication true. Okay? What's key here is that you have to make R true, because when R is true, then negation of R is false. So if you're looking for a counterexample, you want to make sure that your conclusion is false. So you start from there to build your counterexample up. Okay? Okay, what makes this false? Okay, if R is true. Now, given that R is true, can I play with P and Q so that my three premises hold true? If you can do that, then you found your counterexample. Okay? So, very good. Are there any questions? Now, let's try to see, for example, if you look at this for the first time, there's no reason why you would believe that this is a counterexample just by looking at it. Okay, so you may have to do some thinking. And I don't know, looking at it very, for a little bit, I would say, okay, because I have these two guys, this will, from here I deduce P implies R. Okay? Now, I have P implies R and I have negation P. Is that all you need to be able to deduce negation R? This doesn't look like a rule of inference, okay? So, in other words, if you have P implies R, you can deduce that from 2 and 3, okay? Using the transitivity rule. And then you have negation P. Is this enough to say something about negation R? Well, remember, this is the same thing as negation R implies negation P. So this is like saying, I have an implication and I know the last guy. Can I then deduce the first guy? The answer is, well, not necessarily. Remember, our rule says if you know the first, you can deduce the second. But it doesn't tell you that if you know the second, you can deduce the first. So when I get here, I know this is so basic that it should be a rule. If there is no rule that tells me this, I start suspecting that this is probably false. Okay, that this is invalid. And that's when you say, okay, let me go and look for my counterexample. And right here, you can get your counterexample. When does this will fail? Okay, when would this fail? Well, let's see. Let's make these two guys true, but then negation are false, and then you can, it's simpler to look at this one than that one. So how can you make, if negation R is false, then R has to be true. But if R is true, this is false, making this implication automatically true. So I'm free to pick whatever P I want. I don't care. It's not needed for this. So I have to pick it false. So I made this one work. Okay? And that's how you start building your counterexample. So I gave you R must be true, P must be false. Then you return to your previous, to the original problem, and then say, okay, with those cases, I have to say something about Q. It turns out that in this particular problem, Q can be whatever you want. You can make it true, like your classmate did, or you can make it false. It will also work. Okay? Again, there is no one particular way of doing these things. Okay? It's just you developing your problem solving. Okay? I'm giving you the tools, I'm giving you some hints here and there, stuff, general things that you can look for. But at the end of the day, you have to practice and you need to try yourself, okay, to get used to this. It's like factoring. I can be here explaining you how to factor all day, but until you sit down and you do a bunch of factoring problems, then you will be able to look at a problem and know how to factor right away. Okay? I'm doing integrals and doing many of the same factoring because I expect that at this point everybody is able to factor things here. Okay? But that requires some thinking and some experience. Do you understand what I'm saying? Okay. All right. Okay. Of course, unless the problem, if the problem say, argue, determine whether this is valid or invalid, using, without using a truth table, then you have to do it without using truth table, and this is the choice that you have. Okay. But if I don't say anything, if I just give you the argument and I say, determine the validity of this argument, you can do it however you want. You can try this, but remember, if this doesn't come to your mind, you can always try the long way. What's the long way? Do the truth table. This one would be an 8-row truth table. Okay, it's not so bad, but still, 8-row, and we have several columns because there are a bunch of premises and so on. But you can do your truth table. At some point, your implication is not going to be a tautology. At least there will be 2 rows, right? That's going to fail. So a row that gives you false at the end, you can track it back, and then the original values for P, Q, and R, that will be your counterexample. Okay? So understand that you have choices, unless the problem doesn't give you a choice. If I say don't use truth table, then I really want to see if you can do this. Okay? So keep that in mind. All right. Any questions? Yes.
Do you have to memorize like R1, R2, R3, R4?
And as I mentioned, I will provide this to you.
Oh yeah.
So if I require you to use this, I will give you in the exam. There will be a page that will have this, so just take it out and then you have it next to you to use it whenever.
And do we have to write it on the proof, or can we just use it? Like, can we say we're using this one?
Yeah, just like what I did here. When you justify something, you tell me either premise, rule of inference, or if you use something from logic. For example, we got number 5 by doing the contrapositive of 4. If you don't remember the name, but you know that these two things are equivalent, just write here logic. I mean, you should know that you're using something from logic, right?
Okay.
So at least tell me logic, and that way I know that you know what you're doing, even if you don't remember. I don't care if you remember the name or not. I mean, it's nice if you remember, but it's not really important. What's important is the knowledge, okay? As long as you know that these two things, 4 and 5, are the same, then that's all I need. But just tell me logic, okay? Let's try something. Do you understand what I'm saying? Yeah. Okay. When you're writing this format in your house, then you have your notes, you have the books, the internet, everything you want. So you can look, okay, what is this rule that I know but I don't remember the name? Look it up. And then you write it, okay? But on an exam, I don't expect you to know all of these little names all the time. Okay? All right. Questions? So as for this, because I understand, some of these are kind of straightforward, but there are some that are not, like number 8, maybe number 4, looks strange to you, okay? So I will provide this, but for example, the logical equivalences that we did, earlier, these are rule of inference. The logical equivalence, I do expect you to know those. Okay? So like the Morgan's law, those things, I do expect you to know. And they're gonna give you those rules on paper. Okay? All right. Like distributivity, associativity, all of those properties. You don't have to remember the name, but you need to know the properties. You need to know something. Okay. Questions? No? Okay, so then now what we're gonna do is we're gonna try to put all of this together. Oh. So that's fine. It's just that I wrote the solutions in last lecture notes. I'll just copy and paste that one here. I just realized, but it doesn't matter, it's the same thing. I just, anyways, what I have was the same page, I copy and pasted, and then my plan was to fill in here. I just deleted this and put the other one, so that's not a big deal. All right, so now what we're gonna do is we're gonna move to the last section of this chapter in which we're gonna prove, we're going to put everything together. Okay, everything that we have been doing little by little, we're gonna put it together, and then we're gonna start talking about how to write proofs. Okay, how giving an argument, giving a problem, giving a statement, how can you determine whether this statement is valid or not, whether it's true or false. Okay, if it's true, you need to provide a proof. Is it false? If it's false, what do you need to do? You give me a counterexample. Okay, so let's do that, and we're gonna need the knowledge from everything that we have discussed so far. Okay, so this is gonna take today, and then your independent work on Friday. The exam is gonna be next week on Wednesday. Monday I'm gonna start something new, but the reason why I'm doing it on Wednesday is so that if you wanna come and talk to me, ask me questions from the homework, things that you don't understand from this last discussion, you can come. You come to my office hours and you ask me. The office hours are on the syllabus. Okay, I have office hours on Monday in person. I have office hours on Tuesday that are online, but you can show up to my office, but it's by appointment. You need to let me know if you're gonna come or not, so I can be there. Okay, so keep that in mind. All right, so proof techniques. Let's talk about this again. Like the name suggests, this is about proofs. In particular, we're going to lay down the format of how a proof should look like. And then if you go back and you read the very first proof that we did at the beginning, that square root of 2 is not a rational number, it should now make sense to you. Okay? After we talk about these things. All right, so before I start talking about each of the techniques, let us remind something important. So recall a universal statement. So to prove, so these are like some general facts. So to prove a universal statement, and this statement would be for all x, p of x, okay? Of course, there is a domain. So given a domain, okay, so given a domain, to prove a universal statement, what is it that we need to do? So to prove means to show that this is true. So what does it mean for this to be true? You can tell me? We did this in the previous section. What does it mean for this to be true?
That every value in the domain makes p of x true.
Exactly, that p is true for every value in the domain. Yes? So if you want to prove something like this, you need to argue that no matter what x is, p itself is going to be true. Okay? In other words, the way that we will say this, so universal statement, remember, this is true if and only if p of x is true for all x in the domain. Let's say the domain is D, okay, for all x in D. So we write, so we typically start, whenever you have a universal statement, we typically start with the following line. Let x or a, whatever is your favorite letter, be an arbitrary element in the domain. In other words, here you're saying x is whatever you want within our domain, and then you proceed with your argument. Okay? So you can never tell me, imagine that x is 3, and then prove it for 3. Yeah, okay, that works for 3, but how do I know if it works for something else? You have to show that it works for everybody. Okay? So and that's why we say let x be an arbitrary element in whatever domain it is. It depends on the problem you will see in the example. So we begin, let x be arbitrary or something along these lines, okay? Or let x be any element or any number, whatever the problem is. Something that gives the same idea. So let x be arbitrary, be an arbitrary element domain D, then, and then, you argue, and you show, so let X be an arbitrary element, then, etc., and then your job is to, at some point, you would like to say that P of X, whatever P is going to be true. If it's true for this arbitrary X, it means it's true for everybody. Do you understand this? You never assume anything special about X, unless you're covering all the cases. You're going to see that there are some problems in which there are some proof that you may need to say something about X specific, so that's what a proof by cases is. Okay? Because maybe you want to prove a statement, and it will change depending whether X is even or odd, let's say. Then you say, well, that is for all numbers, so you say, well, if X is even, this happens, and now you need to tackle also the odd part. Otherwise, you're not proving for all numbers, you're only proving for the odd numbers, for the even numbers. Okay? But when you combine the two pieces, you get the whole thing, that's fine. All right? Okay, so that's a general idea that we know from before. And then also we have existential statement. Oh, wait. This is to prove this. Now, what do we do to disprove? To disprove for all xp of x, in other words, to show that this is false, that's what it means to disprove, right? What do we need to do?
Just counterexample.
Find a counterexample. Okay? In other words, if you want now, we can formally see what it means. So, we want to show, so I, to show that for all of xp of x is false, is the same as showing that its negation is what?
There exists.
And to showing us its negation is what? If something is false, what's negation? True. So if you want to show that something is false, it's the same as showing that its negation is true. You could try that. That's one technique, by the way. That's proof by contradiction. Okay? So you can show that its negation is true. But now, let's use what we know. What's the negation of for all xp of x?
There exists.
So this is the same thing as saying that exists x such that negation of p of x. In other words, if you want to show that a universal statement is false, you need to then show that this existential statement is true. And how do you show that an existential statement is true? By giving a quick example. The existential statement says there is an x such that this is happening. All you have to do is tell me here is the x. You walk away. Okay? Well, give me an x that makes p not work. Because not p to be true means that p must be false. And that's your counterexample. That's why to prove that a universal is false, we do a counterexample. Why? Because then its negation must be true, and the negation is existential. And the example here is something that makes p fail. Because when p fails, its negation works. Do you understand what I'm saying? Okay, so that's a formality of why to disprove this, you need a counterexample. Okay? So we prove this. So we prove existential by giving an example. Let me write it. Another point here. Existential statement. If you have that exists x p of x, this is true if and only if, there is at least, it could be more, but if there is at least one element in D for which p of x is 2. Okay, so find an example. That's all you have to do. Find an example. Now, if you want to show, and therefore to show that a universal is false, you turn it into an existential. Therefore, you need an example. But because we're countering that, then we call it counterexample. Okay. Now, if you want to show that an existential is false, using this idea now, how would you do it? So, note, to disprove an existential statement, what do we do? So we want to show that there exists xp of x is false. Again, let's apply the same technique that we did above. To show that this is false, what would be an equivalent way of doing this? So this is the same thing as saying that the negation is true. Yes? But now let's break this up more. What's the negation of this?
For all x, not p of x.
For all x, not p of x is true. In other words, if you want to disprove an existential, this turns into a universal, and then you have to show that this universal is true. You have to show that for all x, p doesn't work. That's basically what you need to show. No matter what x you pick, you have an issue with p. Okay? So this kind of gives you how you can tackle problems and how you can approach certain situations. This is very general, but we need this as we move forward. Okay? All right, so now let's get down to more specific ideas. So the most common statements in mathematics are conditional. Like, if something, then you can deduce something else. Okay? So this is most of the statements, many of the statements that you can find that you need to prove. So let's discuss how we do that. So conditionals. So these are proof techniques. Proof techniques. And then the first one, let's talk about conditionals. Remember, conditional is something that looks like P implies Q. Okay? So there are several ways of proving. There is one general way that's called direct method, and then there is the indirect method. Direct method is that you go straight without making any extra assumption. You go straight and you prove a statement. So to prove, what's the idea here? Think about the truth table of the conditional. So we want to show that a conditional is true. So what do we need to show for a conditional to be true? In other words, when is a conditional true? Think about the cases. When is a conditional true? When P is false, I don't care what Q is, right? It's going to be true. And then what's the other one? When both of them are true. In other words, if P is false, regardless of what you're saying here, this will be true. So that means if P is false, this automatically works. So we don't have to worry about that. The only case that we really need to worry about is when P is true, we need to make sure that Q must be true, right? So that's what we do. So when you have an implication, to argue that this is true, what you need to show is that if P is true, then that will give you that Q must be true as well. If that happens, then you're good to go. Because if P is false, then you're done automatically. You don't have to say anything about Q. You understand this? So when you have an implication, the idea is we assume P is true, and then we argue, you know, sometimes it's just one line, and sometimes it's a full page, sometimes it's an entire book. It really depends what sort of statement you're trying to prove, okay? So assume that P is true, argue, and then the hope is that eventually we can say, therefore, Q is true. If we manage to say the magic words, therefore, or and so, as a result, or whatever, then we're done. So that's the idea. Assume the beginning, work towards the and prove that the end is true. Okay? Let me give you some examples so you can see what I mean by this. Examples. So, prove or disprove. Okay? The following. So let's see. For all integers n, again, these are going to be very easy questions, okay? But the idea is to get the format down. If n is even, then n squared is even. Let's see here. First of all, what type of statement is this? This is a universal statement, yes? And then the predicate part, what sort of logic operation do we have? The condition. It is an if-then. Okay, so here you have to mix the universal technique that we said above together with the specific part, because at the end of the day, it boils down to showing that P is true, right? So how do you show that P is true? Well, you have to see what's your P. My P is a conditional. So to show this, you need to assume the premise, and then you prove your conclusion, or the antecedent. Okay? Assume the antecedent, prove the conclusion. Remember, it's called antecedent or premise, your P, at the beginning of the implication. Okay, so let's see how we formally write this down. This is universal, so we need to show that our domain is the integers, right? So we need to show that no matter what n is in the integers, that works. So we begin with the line, let n be any integer, or be an arbitrary integer, okay? That takes care of the universal part. So let n, and you have to use n, you can, let n be any integer. Just by starting with this sentence and saying that whatever I'm about to write, it works regardless of for whatever number you pick, right? Now, something else that you have to be able to, that you need to know is that when you are writing a proof, you need to know the meaning of every single word in your statement. Otherwise, how can you argue something if you don't know what it means? Okay? So before we even continue, let's read the sentence and make sure that we understand every single word here. Okay. This we know. This we know what an integer is. Yes, everybody knows what an integer is. It's 1, 2, 3, 4, 5, or -1, -2, etc., including 0 as well. Okay? So, good. This is a variable. Implication, good. Now, the other word here, I guess, is even. Do you know what is even, like formally?
Divisible by 2.
Even means divisible by 2. How can you write that mathematically?
X times 2.
That means that it's a multiple of 2. Okay? So, for this at some point, we need to use, I guess I'm going to make here, this is not part of the proof, but I need to write it somewhere. So a definition. What does it mean for a number to be even? Definition. An integer n is even if it's divisible by 2. In other words, if there's a multiple of 2, which is to say there is another integer, so n can be written as 2 times that integer. That's what it means to be a multiple of 2. It's 2 times something, where that something is an integer. Okay? It has to be an integer, for example. Is 1 even? No, but I can write it as 2 times 1/2. So you cannot just tell me, oh, 2 times something. No, it has to be 2 times an integer. The problem here is that 1/2 is not an integer. Okay? So an integer n is even if there is, okay, when I say there is, we already know the symbol, so I'm gonna write it, okay? If there exists a k, which is integer, such that n is equal to 2 times k. All right? That's what it means to be an even number. That you can write it as 2 times an integer. Okay? Because eventually we want to argue that n squared is even. So our job is to show that n squared equals 2 times an integer. That's what you want your last line to say in your proof. That n squared equals 2 times an integer. Okay, so now we proceed. This is an implication, so what do? Assume P, prove Q. All right? So let n be any integer. Now, okay, so first of all, I guess we should say here, because n is any integer, we should say here, if n is odd, remember, we need to argue for every integer. So if n is odd, then there is nothing to prove. Why? Why? Because the statement is about even integers, right? So the statement says if n is even, then n squared is even. So if n is odd, then this statement is really not saying anything. In fact, this implication will automatically work because we're starting with something that's false. Because n is odd, this part right here is false. You can say whatever you want with it. Okay? So we don't have to worry about that. Really, what's important is what happens if n is even. So if n is odd, then there's nothing to prove. So now assume that n is even. The reason why I have to write this is because remember at the beginning we said n is any integer. Now I cannot just tell you, oh, if it's even, well, but then if it's any integer, then you would tell me what about when it's odd. So you have to have a line that tells you what happens there. But if it's odd, we don't care because it's not part of the statement. Do you understand this? Okay, so we got that out of the way. Now we are focusing on the even part. So if n is even, assume that n is even. Then what can we say here for sure? This is the argue part that I wrote here. You see? Assume that P is true, then argue, and the job is to deduce Q at the end.
N is equal to 2k.
Exactly. So you can only use what you have. If n is even, the only thing that we can say here is that it's 2 times something, because that's what it means to be even. Okay? So then we know that there is an integer and there is an integer k such that n equals 2 times k. Nobody can take that from us because that's what it means to be an even number. Yes? All right. Now, what can we do from here? What do you think we should do?
Define n squared as 2k times 2k.
Exactly. Let's square n and let's see what we get, right? So then we have this. So from here then, it follows that n squared can be written as 2k squared, right? And then what's 2k squared?
4k squared.
That's 4 times k squared, which is 2 times. Remember, our job is to write it as, we want to write it as 2 times something because that's what it means to be even, right? It's 2 times 2k squared. And here is the important part. So it's 2 times something. What we need to verify now? That this something is what? An integer. So the question is this an integer?
Yes.
Why?
Because an integer is an integer is an integer is an integer.
Because k is an integer. Right? If you square an integer, you get an integer. Multiply by 2, you still have an integer. Okay? So n squared is 2 times something, and 2k squared is an integer. Since k is an integer. Because remember, if k was not an integer, then, I mean, you can always make this work. I can make it work with 1, it's just that you will have a 1/2 here. Okay? And because you don't have an integer here, then you're not going to get an integer always. Okay? So the fact that it's an integer is very important. In this case, an integer. Therefore, n squared is even, because we just showed that it's 2 times an integer. And we're done. And typically, to see now, typically proof are written like this in paragraph form, and to see now that you're done, you write like a little square filled in. Okay, the end of the proof, because then you write all the stuff. You want to say that after this, it's not part of. You don't put a period because we have a bunch of periods in this paragraph. Okay, so we do a square to show the proof is done. Did you understand this? Okay.